All right, I'm going to talk a little bit about circular motion. In case the name doesn't give it away, it's objects that move in circle-like paths. You might run across a little different nomenclature for it. You might see something like uniform circular motion. The only thing that really means, and you can read the definition that's up there, it says an object that moves in a circle at a constant speed. And the constant speed part is important because it implies that the magnitude of the velocity remains constant. But if you're traveling in a circle, the biggest thing that happens is you're changing direction. And in unified circular motion, because you are changing the direction of your speed, then that means that the velocity itself is not actually constant. Okay, the magnitude of the speed is, but not the direction. Okay, now we know that if an object is changing its velocity, then it is undergoing what is called an acceleration. So we have a new term, something called centripetal acceleration, or sometimes referred to as radial acceleration. And on the screen again it says that the object undergoes an acceleration because it is changing directions. So if I was just referring to some object traveling in a circular path, okay, or say I looked at it here and here, a reminder that if it's traveling in a circular path at any point, and actually let's curve this off, let's make this the very top point, let's not worry about that one. At any point, the velocity of the object is always tangent to the circle. So if this was the point up top here, it would have a velocity off in this direction. This would be v1. Okay, and then down here, it again would have a velocity that is tangent to the circle. So this would be, say, v2. So notice that the direction of those velocities have changed. Okay, and I'm going to try to draw this as best as I can, but if we know there's a change in velocity, in this case it would be v2 minus v1. So from vectors, if I took a look at this, this is v2, and if I want to subtract v1, that would be back this way, and you end up with a resultant vector here that is aimed towards the center of the circle. And my circle's kind of crappy here. If I extended it out, it would look more as if it was towards the center. But this change in velocity is always directed towards the center of the circle. Okay. Now this results in an equation, and you'll derive this in your lab that you do. But essentially, it has a fairly simple equation that just says AC is v squared over r. You might also run across it as AR for radial. But for the most part in this class, we'll stick with this. Okay. Now, as we get through this unit, there's going to be a couple other things that are fairly important to discuss, things that you're going to see. We'll run across terms like frequency and period, and you've probably heard these terms before. You've heard of period from Pendulum Lab that we did early in the year. But frequency, which gets a little fancy F here, is in reference to the number of revolutions per second. And then the period, which is a big capital T, that's going to show up in some other equations that we see, says it's the time required for one revolution. And then this is their relationship. This is how those two things are actually related to each other. If you notice, they are inverses. T is 1 over F, and we could say F is 1 over T. So an example frequency might be that something revolves at 5 revolutions per second. Okay, then the period would be the inverse of 5, which would be the 1 over 5, or 0.2 seconds per revolution. So that's how those two things are related. One thing about unified circular motion is that you are moving at a constant speed. Now, constant speeds were always written as v equals delta x over t, or if you're an IB, it would be v equals s over t. Either way, in unified circular motion, when something's traveling in a circle, the distance that it travels is the circumference. So basic formula for then the distance that it travels would be the circumference formula, which is 2 pi r. So in unified circular motion, we will write the velocity, this is a constant velocity, as 2 pi r over the period, because that would be the time it takes for each revolution. So this is in essence the distance it travels over the required time to travel. Okay. Now, again, if we look at this particular equation, AC is v squared over r. Oftentimes a little helpful or useful connection that you might have is, what if I substitute this in for v? And if you do that, then you would get 2 pi r squared over t squared r, because I have to square this whole thing, right? Well, then that would give us 4 pi squared. The r squared and one r on the bottom leaves r on the top with t squared on the bottom. So this might be a useful little connection for problem solving stuff. Okay? All right. So the next thing, where there is an acceleration, there must be a net force. We learned last unit that if an object accelerates, then there must be an unbalanced force acting on it. That is now called the centripetal force. Now, I really want you guys to try to focus on thinking centripetal force is really the net inward force. Okay? It is the net force towards the center of a circular path. Okay, so again, if I look at my centripetal acceleration equation, excuse me, acceleration in last unit was always the sum of the forces was equal to m times a. Okay, well, now let's try to think of it as the centripetal force, because it is a net force, is equal to m times the centripetal acceleration. So if I rearrange this equation so that AC is Fc over m, and I now substitute in Fc over m for AC, then I would get Fc over m equals v squared over r. Or oftentimes centripetal force is simply written as Fc is mv squared over r. That's the most common equation that you will see for centripetal force. Now again, I want to reiterate that the centripetal force is not a new type of force. Just like unbalanced forces were not new forces. They were simply the difference between things. So again, you should never be drawing in f of c on a free body diagram. Just like you never wrote in fu on a free body diagram, okay? So I want you to try to think about this here. If I had a ball that was on a string, and let's say I'm twirling it horizontally, so it's above my head and I'm swinging it around my head, okay? A ball on a string, what force is actually causing it to stay in that circular path? Well, it's the string, right? So in this case, the centripetal force might be a tension force. And that would be, of course, if it was perfectly horizontal, which is hard to do. How about the moon going around the Earth? Why does it stay in a circular path? Well, that's because of the gravitational attraction. So in these cases, these are centripetal forces, okay? Which means you can set them equal to each other. A car around a corner, why when you make a turn do you not just stay going in a nice straight line? Okay, you're able to turn the corner because in that case there's friction between the tires and the road. Now in that case, friction is the centripetal force. Okay, and then the last little thing that I have on here says that centripetal force is not always just the result of one force. It might not be just the tension, just the gravitation, or just the friction. Therefore, I want you to think of it more as it's a net inward force, or the sum of the forces towards the center, or the unbalanced force acting on the system towards the center of the circle. I can't stress it enough that it is the net inward force towards the center of the circle. Okay, so hopefully that little blurb there hopefully makes you understand a little bit about circular motion, and then we'll do some more in class. All right.